everyone, and welcome to the deep dive. One of our listeners has been really curious about electrons and sent over this fascinating article about them. So today, we're going on a deep dive into the world of, well, electrons.
These tiny particles
Uh,
that we often take for granted.
yeah, but they're kind of a big deal. I mean, think about it. They're literally everywhere and involved in, well, practically everything from
Mm.
powering our devices to
The forming the bonds that hold matter together.
yeah, exactly. So get ready to unlock some of the mysteries of these subatomic superstars as we cover their discovery, their kind of crazy quantum behavior, and yeah, even how they shape our technological world.
It's going to be a fascinating journey.
Yeah, I'm excited. So let's rewind the clock way back to 1897. That's when J.J. Thomson first discovered the electron.
Ah, a pivotal moment in scientific history.
Totally. The article mentions something called the plum pudding model. Can you break that down for us?
Well, back then, scientists were still trying to figure out what atoms were made of,
Right.
right? So Thomson's experiments with cathode rays, these beams of, of negatively charged particles,
Okay.
led him to believe that these particles were actually, fundamental building blocks of matter.
So that's where the electron comes in.
Exactly. He called them electrons, these tiny negatively charged particles. And he imagined them embedded within a positively charged sphere, like plums scattered in a pudding. Hence, the plum pudding model.
Ah, okay. So like little negative bits in a big positive blob. That's actually kind of funny to picture now.
It is a bit simplistic looking back, but hey, it was a groundbreaking idea at the time. It was our first glimpse into the structure of the atom.
But of course, our understanding didn't stop there, right?
Oh, absolutely not. Science is all about refining our models as we learn more.
Right.
So just a few years later, Ernest Rutherford comes along and conducts his famous gold foil experiment, which, it really shook things up.
Oh, yeah. What did he do?
He bombarded a thin sheet of gold foil with alpha particles, basically helium nuclei, which are positively charged. And he expected most of them to pass straight through the foil, like bullets through tissue paper.
Makes sense, I guess, if the atom was mostly that positive pudding stuff.
Right. But to everyone's surprise, some of those alpha particles bounced back, some at sharp angles.
Whoa, really? What did that mean?
It meant that the atom wasn't a uniform pudding at all. There had to be something small, dense, and positively charged concentrated at the atom's core to deflect those alpha particles so dramatically.
So that's where the nucleus comes in.
Exactly. Rutherford proposed a new model of the atom one with a tiny, dense, positively charged nucleus at its center, and with electrons orbiting around it, kind of like a miniature solar system.
So we went from plum pudding to a teeny tiny solar system. Pretty big shift.
Huge. It completely revolutionized our understanding of atomic structure. And this model, with its vast empty space between the nucleus and the orbiting electrons, well, that's the basis of the atomic model we still use today.
Cool. But now the article takes us even deeper into this really weird world of quantum mechanics. It mentions wave-particle duality, and I'm already feeling a little lost. So are electrons waves or particles? Which one is it?
That's the thing about quantum mechanics. It often defies our everyday intuition.
No kidding.
The answer is, well, both.
Wait, what? How is that even possible?
Electrons exhibit properties of both waves and particles. It's not that they're switching back and forth. It's more like they have this dual nature. Like it's not what an electron is, but more how it behaves.
Okay, I think I need an example to wrap my head around this. How can something be a wave and a particle at the same time?
Okay, imagine a ripple spreading across a pond.
Yeah,
That's kind of like the wave-like behavior of an electron you see.
I think so.
But now, picture a tiny marble zipping
Wow.
around. That's more like the particle-like behavior. The ripple doesn't suddenly turn into the marble. It's just that electrons, well, they behave like both of those things simultaneously.
So it's not one or the other. It's like both at once. My brain hurts.
It's definitely a mind bender. And this leads us to Heisenberg's Uncertainty Principle, one of the cornerstones of quantum mechanics. It states that we can't know both the position and momentum of an electron with perfect accuracy at the same time.
So we can't know where it is and how fast it's going at the same time.
Basically, the more we try to pin down its location, the less we know about its momentum, and vice versa. It's like trying to get a firefly in a jar. As soon as you think you have it, it's already moved somewhere else.
Okay, that makes sense, kind of. So if we can't pinpoint an electron's exact location, how do we describe its position within an atom then?
Ah, that's where the concept of atomic orbitals comes in.
Orbitals. Yeah, I remember that word from chemistry class.
Instead of thinking of electrons as orbiting the nucleus in these neat little paths like planets around the sun, we have to think of them as existing in these fuzzy clouds of probability called orbitals.
Okay, so not a planet orbiting the sun, but more like a blurry cloud. I'm trying to picture it.
Exactly. These orbitals are three-dimensional shapes surrounding the nucleus. Each orbital has a different shape and a different energy level. And these shapes represent the regions where an electron is most likely to be found.
So instead of a defined path, it's more like a probability map. Like if you could take a snapshot of the electron over time, it'd be most likely to show up in these specific zones.
Exactly, like a heat map, showing where it's most likely hanging out. And to make things even more interesting, each orbital can only hold a certain number of electrons.
Okay, so that's starting to sound a little more familiar. This is leading us to electron configuration, right? Like how the electrons are arranged within an atom.
You got it. Electron configuration is like a set of rules dictating where each electron lives within the atom's orbital structure.
Ah, okay. I vaguely remember those rules from high school chemistry. The Aufbau principle, Hund's rule, the Pauli exclusion principle.
Yeah, those are the ones. Each of them helps us to understand how electrons fill those orbitals and how they behave within the atom.
This is so cool. So those seemingly abstract rules actually govern how every atom in the universe is structured.
Absolutely. And understanding these rules is key to understanding how atoms bond with each other to form molecules and how they interact with light and energy.
And that's kind of everything, isn't it? It's like the foundation of chemistry and physics. This is already blowing my mind, and we haven't even touched on chemical bonding or the amazing technologies that exploit the unique properties of electrons.
We've got a lot more to uncover, but I think it's time for a short break. We'll be back in a bit to delve deeper into the fascinating world of electrons and explore how they shape our world in remarkable ways. So before the break, we were talking about how electrons are arranged in these orbitals around the nucleus.
Right, like those fuzzy clouds of probability.
Exactly. And, all those rules about how electrons fill those orbitals, it might seem kind of abstract,
Yeah, a little bit.
but it all leads to something amazing, chemical bonding.
So this is where things start to get really interesting because that's how atoms connect to form molecules, right? It's like the glue that holds everything together.
Precisely. And there are different types of bonds, each with its own unique characteristics based on how those electrons interact.
Right, like ionic bonds, covalent bonds.
And metallic bonds.
Yeah, metallic bonds. Those always seemed a little mysterious to me. But let's start with ionic bonds, maybe. Those are the ones where electrons are transferred from one atom to another.
Exactly. Think of it like this. Some atoms really want to gain electrons to achieve a more stable electron configuration, while others are more than happy to give them away.
Okay, makes sense.
So in an ionic bond, you have one atom that's really electronegative, meaning it has a strong pull on electrons.
Like it's an electron hog.
Yeah, kind of. And then you have another atom that's more electropositive, meaning it's okay with letting go of some electrons.
So what happens is the electron hog just snatches an electron from the other atom.
Well, it's more like a transfer. The electronegative atom gains an electron, becoming negatively charged, and the electropositive atom loses an electron, becoming positively charged.
Oh, right. So they both become ions. And then opposite charges attract. So that's what creates the bond, that electric attraction.
Exactly. And that attraction is what holds the two ions together, forming an ionic bond. It's like a magnetic attraction.
Yeah, that makes sense. So ionic bonds, it's all about that give and take, that electron transfer. What about covalent bonds? Those are a bit different, right? They share electrons instead of transferring them.
You got it. Covalent bonds are all about sharing. In this case, you have two atoms that both want to gain electrons to achieve a more stable configuration.
Okay.
So instead of one atom completely hogging the electron, they decide to share it.
Like they're playing nice and sharing their toys.
Exactly. They overlap their orbitals, and the shared electrons spend time around both nuclei. This sharing creates a bond that holds the atoms together.
So in ionic bonds, it's like a tug of war where one atom wins the electron. But in covalent bonds, it's more like a partnership where they're both holding onto the electron together.
That's a great way to put it.
Okay, so that's ionic and covalent bonds. But now let's tackle those mysterious metallic bonds.
All right, metallic bonds. These are a bit unique because the electrons aren't localized to a specific bond between two atoms.
So they're not sharing between just two atoms. What are they doing then?
Imagine a giant pool of electrons shared among a whole bunch of metal atoms.
Like a massive electron party.
Yeah, kind of. The electrons are delocalized, meaning they're free to move around throughout the entire metal structure.
So it's not like they're stuck between two specific atoms, they're just like roaming free.
Exactly. And this sea of delocalized electrons gives metals their unique properties, like, for instance, their ability to conduct electricity so well.
Oh, right, because the electrons can flow freely through the material. It's like they have an electron highway to travel on.
That's a great analogy. And this free movement of electrons is also what gives metals their shiny, lustrous appearance. When light hits a metal, those delocalized electrons can easily absorb and re-emit the light energy.
Ah, so that's the science behind the bling. So those tiny electrons are responsible for both the electrical conductivity and the shiny look of metals.
Exactly. It's incredible to think about how much those tiny particles influence the macroscopic properties of materials.
It really is. But, we've talked a lot about how electrons behave in atoms and how they form bonds. But what about how we've used our knowledge of electrons to create amazing technologies? The article mentioned things like semiconductors and electron microscopes.
Ah, yes. Those are fantastic examples of how our understanding of electrons has led to groundbreaking technological advancements.
Let's start with semiconductors. I know they're super important for electronics, but I've always been a bit fuzzy on how they actually work.
Semiconductors are materials that have electrical conductivity somewhere between that of a good conductor, like a metal, and an insulator, like rubber or glass.
Right, right. So they're not great at conducting electricity, but they're not terrible either.
Exactly, they're kind of in between. And that's what makes them so useful. Take silicon, for example. It's the most common semiconductor used in electronics.
Okay.
By itself, pure silicon isn't a great conductor. But here's the cool part.
Yeah.
If we add tiny amounts of impurities, like phosphorus or boron, to the silicon crystal, we can change its conductivity.
So we're like doping it, like adding a little bit of something extra to change its behavior.
Exactly. And by carefully controlling the type and amount of impurities, we can fine-tune the silicon's conductivity and create regions where electrons flow easily or regions where they're blocked.
So we can kind of control the electron flow within the material, like
Yeah.
creating little electron pathways.
That's a great way to think about it.
Yeah.
And this control over electron flow is what allows us to create transistors.
Oh, transistors. Those are like the tiny electronic switches that make all our gadgets work, right?
You got it. Transistors are the fundamental building blocks of modern electronics. And by combining billions of these tiny transistors onto a single chip, we get integrated circuits, the brains behind our computers, smartphones, you name it.
Wow, so our entire digital world is basically built on this ability to manipulate the flow of electrons within these tiny semiconductors.
It is. And that's just one example. Let's talk about electron microscopy, another fascinating application that's revolutionized several fields.
Yeah, the article mentioned that electron microscopy. Isn't that how we can see things at like super tiny scales? Things that are way too small to see with regular microscopes.
Exactly. It's like having a superpower to see the invisible world. Instead of using light to illuminate the object, we use beams of electrons.
Why electrons, though? Why not just stick with light?
Well, light has a limited resolving power because of its wavelength. It's simply too big to see the tiniest structures. Electrons, on the other hand, have a much smaller wavelength, which allows us to see things at a much finer scale.
So it's like using a much finer tool to probe the microscopic world.
Precisely. With electron microscopes, we can see things like individual atoms, the detailed structure of viruses, and even the intricate arrangements of atoms and materials.
That's incredible. We're using electrons to explore the world at a whole new level of detail.
It's truly remarkable, and it wouldn't be possible without our understanding of how electrons behave and interact with matter.
Okay, so we've gone from the basic structure of atoms to how electrons form bonds to how we're using them to explore the invisible world and build amazing technologies. This is seriously mind-blowing stuff. But the article hinted at something even more futuristic: quantum computing. Is that something we can even wrap our heads around?
Well, quantum computing is definitely a whole other level of mind-bending, but it's built on the same foundation, understanding the bizarre world of electrons and their quantum behavior.
All right, bring on the quantum weirdness. I'm ready to dive in.
Okay, first, we need to talk about one of the most fundamental principles of quantum mechanics, superposition.
Superposition. That sounds super complicated.
It is a bit of a head-scratcher, but I'll try to keep it simple. Basically, superposition means that a quantum particle, like an electron, can exist in multiple states at the same time.
Wait, what? How can something be in multiple states simultaneously? That doesn't make any sense in our everyday world.
It doesn't, but that's the beauty of quantum mechanics. It operates under a different set of rules. Think of it like this. Imagine a coin spinning in the air. Before it lands, it's neither heads nor tails, right?
Hmm.
It's in this blurry, in-between state.
Okay, I kind of get that.
In a similar way, an electron in superposition is in this fuzzy, undefined state until it's measured. It's like it's both possibilities at once.
So it's like the act of measuring forces it to choose a state.
Exactly. It's
Yeah.
called wave function collapse.
Mhm.
But before we measure it, it's truly in multiple states simultaneously. Pretty wild, huh?
Yeah, my brain is definitely starting to hurt. But how does the superposition thing relate to quantum computing?
Well, that's where the concept of a qubit comes in.
A quick.
Yeah, a qubit is the basic unit of information in a quantum computer. It's like the quantum version of a bit, which is the basic unit of information in a classical computer.
Oh, right. Like a bit is either a 0 or a 1.
Exactly. But here's the difference. A classical bit can only be either 0 or 1 at any given time. A qubit, on the other hand, can be both 0 and 1 at the same time, thanks to superposition.
So it's like a bit that's gone quantum, it can hold multiple values simultaneously.
Exactly. It's like it's exploring all possible values at once.
Yeah.
And this ability of qubits to be in multiple states at the same time gives quantum computers a massive advantage over classical computers.
I'm trying to wrap my head around how that actually works. So if a qubit can be in multiple states at once, does that mean it can perform multiple calculations simultaneously?
You got it. That's the power of quantum computing. It's like being able to explore every possible solution to a problem at the same time instead of having to go through them one by one like a classical computer does.
That sounds unbelievably powerful. I can see why people are so excited about quantum computing. But how do we actually build these quantum computers? How do you control and manipulate these qubits?
Well, that's the challenge. There are different approaches being explored, but it's a very complex and rapidly evolving field. It all boils down to carefully controlling and manipulating the quantum states of individual particles, like electrons, using things like lasers, magnetic fields, and superconducting circuits.
It sounds incredibly difficult. It's amazing that scientists are even able to do this.
It is. But the potential payoff is huge. If we can crack the code of quantum computing, it could revolutionize fields like medicine, material science, artificial intelligence, and even cryptography.
It's mind-boggling to think that we've come so far from those early models of the atom to potentially harnessing the power of quantum mechanics to solve some of humanity's greatest challenges.
It's an incredible testament to human ingenuity and our insatiable curiosity about the world around us. And it all started with that tiny but mighty electron.
It really is amazing. From those early experiments with cathode rays to the potential of quantum computing, it's clear that the electron is a fundamental building block of our universe.
Absolutely. And the journey of understanding this tiny particle has led to some of the most profound scientific discoveries and technological advancements in human history.
So, to our listener who wanted a deeper dive into the world of electrons, I hope we've given you a new appreciation for these tiny particles that are both fundamental and profoundly impactful.
And I hope this deep dive has sparked your curiosity to explore even further. There's so much more to discover about the fascinating world of electrons and their quantum behavior. Who knows what amazing breakthroughs await us in the years to come.
That's a great thought to end on. Until next time, keep those brains buzzing, and thanks for joining us on the deep dive.
So we've been on quite the journey, from those early models of the atom to the incredible potential of quantum computing. I mean, who knew electrons could be so fascinating, right? It's amazing how much these tiny particles have shaped our understanding of the universe, driven technological innovation.
Yeah, it's mind-blowing. But I guess our understanding of electrons is still evolving, right? Like, what are some of the big questions that scientists are still trying to figure out?
Oh, there's still so much to explore. One area that's really exciting is quantum materials. You know,
Quantum materials?
yeah, these materials have really exotic properties, all thanks to the collective behavior of electrons.
So it's not just about how individual electrons behave, but how they all work together.
Exactly. Like, think about superconductivity. You know how some materials can conduct electricity with absolutely zero resistance at super low temperatures?
Yeah, that's always seemed kind of magical to me.
It is pretty wild, and it all comes down to how the electrons are interacting with each other in these materials. Or take topological insulators, for example.
Okay, topological insulators. Now, those sound really complicated.
Kind of strange. They can conduct electricity on their surfaces, but not through their interiors.
Whoa, really? Like a wire that only conducts electricity on its outside?
Yeah, kind of. It's all thanks to the way the electrons are arranged and how they interact with the material's structure.
So these quantum materials, they could be used to create some pretty amazing technologies, right?
Oh, absolutely. They have the potential to revolutionize everything from energy storage to computing. And that's not all. There's also a ton of research going on in developing new quantum technologies. We talked about quantum computing, but there's also quantum communication.
Quantum communication. What's that?
It's about using quantum mechanics to create ultra-secure communication networks. Like imagine a network where it's physically impossible to eavesdrop on the communication because any attempt to intercept the message would actually change the message itself.
So like a totally unhackable communication.
Yeah, pretty much. It's still early days, but the potential is huge.
Wow. And I guess quantum sensing too, right? Didn't the article mention something about that?
Yeah. Quantum sensing uses the extreme sensitivity of quantum systems to measure things with incredible precision. Like, imagine sensors that can detect tiny changes in gravity, magnetic fields, or even time itself.
That's just, wow, I can barely even imagine the possibilities. It seems like the future of technology is going to be all about harnessing the power of the quantum world.
I think you're right. And it all started with that tiny electron. It's incredible to think how far we've come in our understanding from those early experiments with cathode rays to the potential of these mind-blowing quantum
It
technologies.
really is. I mean, our deep dive today has given me a whole new appreciation for electrons. They're not just these abstract particles in some textbook, they're the key to understanding so much about our world.
I totally agree. And I hope our listener who is so curious about electrons feels the same way. There's still so much to learn, but that's what makes science so exciting. There are always new mysteries to uncover and new discoveries to be made.
Exactly. So, to everyone listening, we hope you've enjoyed this deep dive into the amazing world of electrons. Keep those brains buzzing, and who knows, maybe one of you will be the next to unlock the secrets of the quantum world. Until next time, thanks for joining us on the deep dive.